So I'll be speaking today about dynamic matching in school choice, efficient seat reassignment after late cancellations. This is based on joint work with Itai Feigenbaum, who is now at CUNY, and Yash Kanoria and Jay Seth Raman, who are at Columbia University.
And Yash was one of ours.
Yes, Yash was a postdoc here. And I asked him about his experience, and he said he did some of his best work while here, so he remembers it very fondly. Oops, give me a sec. There we go. Okay. So let me briefly introduce you to the school choice problem. I like to think of school choice as an assignment problem. We're trying to figure out how to put students in schools, but the idea is we want to let students choose where they go to school, because maybe they have private information about which schools they prefer, which schools are better for them. Maybe different students would do better at different schools, and so by using their preferences, we can achieve a better assignment. And so there's a theory behind how to do this assignment that was first developed by Belinsky and Sonmez and Abdulkadiroglu and Sonmez in about 2003. It goes as follows. Students have preferences. You should think of these as rank-ordered lists. So Alice here prefers the blue school, so the orange school, so the yellow school. On the other side of the market, we also have something we call priorities. The idea here is we're not just letting the students choose willy-nilly where they want to go to school. Maybe we also have some central objectives that we're trying to achieve, some things that we think are good from a global perspective. So maybe we want students to be able to attend schools that are close to them, or where their siblings go. And so we impose these in the form of priorities, perhaps to students who live in the neighborhood of a school, or who have a sibling at the school. And now the goal is to let students choose their school while respecting priorities. That is,
So students are just rank ordered, they have no utility. But the priorities, should I think of them as real numbers that I sort of think social welfare is X?
You should think of the priorities again just as an ordinal I have equivalence classes. Yes, I have equivalence classes of students. All the students who live in the neighborhood and have a sibling. All the students who just live in their neighborhood, so on and so forth. Yes. Okay, and now we want to let students choose their school while respecting priorities. So students with high priority should be assigned over students with lower priority, all things equal. And if this is the solution we're aiming for, then the theory also prescribes a way to reach it. We can run the Gale-Shapley Deferred Acceptance algorithm. You might know this from the context of the medical residency match, where it's used to match residents to their hospital placements. Another nice thing about the school choice problem is it's a setting where theory really informs what's done in practice. So in cities all over the US, including New York City, Boston, and Denver, just to name a few, deferred acceptance is currently used in a centralized round of school seat assignment in the public school systems. So for example, in New York City, every year about 80,000 students are assigned to 9th grade seats. They submit their preferences for these seats in December, and then they're assigned via a central round of deferred acceptance in March. And so what the theory tells us is that this gives us the most efficient assignment that respects priorities, where the notion of efficiency should have in mind is Pareto efficiency, where if I want to improve the assignment of any one student, it would either have to be at the expense of another student or violating priorities. Okay, so this is great. We have some nice, rich theory behind school choice. It's currently being used in practice. What is there left for me to talk about today? Yeah. Ordinal. Yeah. So what am I going to talk about today? Well, I'm going to take a look at this time period here between March and September. The question is, the first round of assignment is done 6 months before the start of the school year. What do things look like during these 6 months? Okay, and one thing we observe is that students typically find out about their outside options. So they learn about their private school options, their charter school options. And so every year, about 8,000 seats are vacated between March and September. That is 10% of students who were assigned a high school seat in March choose not to use it by the time that school starts. And so even though we have all of this really nice theory, what we see now is that by the time the start of the school year, we now have an inefficient assignment in the sense that we have empty seats and students we could reassign to those seats and improve their assignment without violating the priorities. So at a high level, our goal today will be to give a systematic way of performing the reassignment process in such a way that we can reach an efficient assignment at the start of the school year. Before I tell you what we do, let me first outline a little about what's done in practice in many of these school choice systems. The vacated seat problem is very real in a lot of these settings, and so most of them use what we call a waitlist system, where students are waitlisted at all the schools that they prefer to their first round assignment. And then when students leave the system, these waitlists are implemented in a decentralized fashion. You should think of principals calling the students on their waitlist and asking if they still want to come to the school. So just as a quick example here, I have just 4 schools, just 4 students, and all the students prefer the schools in the order 1 to 2 to 3 to 4. Okay, and so the waitlist would look something like this, where, for example, student 3 prefers schools 1 and 2 to his current assignment, and so he's on the waitlist for both of those schools. So let's say Alice here goes off to private school. Then what happens now is school 2, well, if she tells school 2 that she goes to private school, then they now know they have a vacant seat. They can call the first student on their wait list, student at school 2, ask, do you want to come to my school? He says yes. Okay, he lets school 3 know. School 3 now has an empty seat. They can ask the first student on their wait list, do you want to come to my school? She says yes. Okay, in this particular case, this is how we would reach the efficient assignment. But in general, you can see that this might actually lead to a lot of congestion in the system. Just one student leaving the system can have a chain effect where we have this, what they call musical chairs of reassignment. On top of this actually leads to a very costly reassignment process. This is because we actually find out about the majority of vacated seats after the start of the school year. That is, we get to September, we look at the first week of school, students aren't showing up, and we think, okay, maybe they don't need this seat anymore. Okay? So these chains of reassignment are starting after the start of the school year. In fact, they currently go several months, 2 months into the school year, at which point there's a hard stop. So reassigning students months into the school year. Obviously, this is very costly for the students who are being moved around, but also costly for administration because they don't know which students will be at their school or even how many students will be at the school. In fact, you might have noticed that New York City kindergarten is the only New York City system that uses wait lists. This is because in the middle school and high school systems, they used to have a wait list system up until about 5 or 6 years ago. Then they decided it was just too chaotic, and they got rid of it. And so now the first round in March is essentially the final round. On top of this, this decentralized waitlist system leads to rather poor allocative efficiency because it's just not enough time to go down all these phone calls and reach the efficient assignment. Okay, so our goal will be to design a seat reassignment mechanism that addresses all of these issues. We want to smooth out the operation, so we want to minimize congestion. We're going to do that by minimizing reassignment. Okay, you might think, okay, we could just not reassign any students. That would achieve that. And so we want to minimize reassignment while still achieving this high ordinal efficiency, where students are assigned to the schools they most want according to their reported ordinal preferences while still respecting priorities. On top of that, we also want the system to have good incentives, so students are entering in both rounds and giving us their real preferences. It's in their best interest to do so. Okay. On top of that, there are also some additional desirable properties of the first round of assignment. And so we want to, first of all, keep the same first round because it's doing a fairly good job of assigning 80 to 90% of the students. And then also keep the properties for the final assignment.
So a couple questions. So are you going to assume that preferences stay the same?
We have some assumptions. I'll get to them in a few slides. Yeah. Essentially, yes. Yeah.
There's a bunch of people that don't participate and then have to go to school, so then they have to be assigned.
So we're not considering in our model arrivals. Our model is really for thinking about departures due to outside options. Yeah, so I'll get into the specifics of how we model that in a few slides.
In practice, though, do people think they're going into private school when they don't? Or why do people arrive in practice?
Typically, people arriving are people moving into the city. And then actually another big arrival group is people who are uninformed and don't know that they need to be part of the really early process, so typically disadvantaged groups. And so there are some delicate issues on how exactly you would want to incentivize early arrival, but also not disadvantage people who just don't have information. So that's one of the reasons we decided not to model that for now. I think there are some additional issues
I
there.
asked if the second round fixes could affect the decision to participate in the first place.
Right.
It could be strategic to not participate in the first round, because then they're trying to help sort everybody out in the second round. And so,
Yeah, perfect. So I will get to the strategic issues, and when I say that we have good incentives, what I mean is that you'll want to arrive and give me your true preferences in the first round, and this will actually be a dominant strategy in our model with respect to both your first and second round outcome. Yes, but as you mentioned, this requires some assumptions on how your preferences change between the two rounds, some kind of consistency. Okay. And so at a very high level, yes, question? Okay, we introduce a single mechanism that achieves all of these properties. But to do so, we first show a class of mechanisms with desirable properties. We call these the Permuted Lottery Deferred Acceptance mechanisms. And the key idea here is that we have these indifference classes in the school priorities, and we currently do some randomization in the first round of assignment within these classes. And so we can cleverly correlate the randomization in the two rounds to achieve different objectives. We'll provide a characterization for this class of mechanisms in terms of their incentive and efficiency properties. Next, we'll show how to optimize over this class of mechanisms. We'll provide a sufficient condition under which all of them give equivalent assignments from the perspective of the final round. So we're just interested in looking at what happens to the student over the course of the whole 9 months from their initial input to their final assignment. And then all of these mechanisms are equivalent by any measure of efficiency you might have. And so what this means, the only thing that we need to care about now is, well, how close is the first round to the second round? And we'll show that the reverse lottery mechanism minimizes reassignment. Finally, we'll also have some simulations using New York City Public High School data. These support our theoretical findings, and I'll also talk about some practical implications and what we're doing with New York City and Boston Public Schools. Let me just quickly flag that these are not the only possible solutions to the issue I raised. I should think of these as kind of things we could do even in the first round of assignment to address what is essentially a problem of incomplete information. Right? I come to the first round of assignment, people don't know what their outside options are. And so maybe I can just assign seats later, after people know their outside options. This gets rid of the whole issue, right? Or maybe I can do some sort of yield prediction. Ooh, let me not block the screen. I can do some sort of yield prediction where if I know that 10% of students are going to drop out of the system, then I just oversubscribe all the schools by 10%, and the students leave, and then I'm left with a good assignment. Okay? And so obviously I see some laughter. There are some issues with both of those in practice. Let me, in the interest of time, not spend too much time discussing these. Happy to talk about them offline. I just want to stress that what we're doing today is looking just at how we would coordinate a second round of assignment, a reassignment. And we think of this as something we could do in conjunction with these measures in the first round. What I'll show you is that by coordinating reassignment, we can simultaneously maximize welfare and minimize reassignment while providing correct incentives for the students to tell us their true preferences in both rounds. And the nice thing, I think, is that we can achieve all of this by making just a small change to the existing system. And so this was actually fairly crucial for getting buy-in in practice. A quick slide on related literature. On the left here, you should think of this as a snapshot of a broad and vast literature on school choice in one round of assignment. Okay? And so there's a lot of stuff in the mechanism design economics literature doing what I think of as characterizing mechanisms based on their qualitative properties. So let's say we want a mechanism that's strategy-proof, some notion of fairness, some notion of efficiency. What should these mechanisms look like? And so we do a similar thing in a reassignment setting. We propose a class of reassignment mechanisms with some desirable properties and show that they're the only mechanisms with these properties. There's also a growing literature in operations research that looks more at what if we have quantitative objectives, how do we start optimizing over those? And so there are a couple of papers that provide a framework for doing such optimization. The closest to ours are these papers, which look at a policy lever, specifically how we can trade off between different measures of efficiency when using tie-breaking the priorities. Okay, this is the randomization I was referring to earlier. And so we'll be also using clever tie-breaking to achieve minimal reassignment while maintaining the same efficiency in the reassignment process. A little on reassignment and school choice. There actually aren't that many papers on that topic in particular. These are some of the papers looking at the problem of dynamic stable matching. And a lot of these papers are caught up sort of in what does it mean to be stable in a dynamic setting? What does strategy proofness mean when your preferences are possibly changing over time? And so we're able to sidestep both these issues by first moving to a continuum model. So we're looking at the effects of aggregate population reports and actions instead of individual students. And then we also have some assumptions on preferences in order for strategy proofness to be a meaningful concept. Okay. So today I'll tell you first informally about our class of reassignment mechanisms. Then I'll present the model and show how to optimize over this class of mechanisms. And then I'll also show you some simulations using New York City public high school data and talk a little about where we're going with this. Okay, so without further ado, here's our class of reassignment mechanisms. We call them the Permuted Lottery Deferred Acceptance mechanisms. They're based on the Gale-Shapley deferred acceptance algorithm. This algorithm takes as input students' strict ordinal preferences over schools and schools' strict priorities over students, and then produces an efficient allocation in the sense of Pareto efficiency that respects priorities in the following way. I'm going to describe a cutoff description of this algorithm that was proposed by Azevedo and Jacob Leshno in 2016. The idea is that every school has an admissions cutoff. Students above the admissions cutoff for a school, that is, students who have sufficiently high priority at that school, have that school in what we call their virtual assortment. This is the set of schools that you could choose to go from if you wanted to. And then students go to their favorite school in their virtual assortment. And the idea is that deferred acceptance helps us find the cutoffs where the demand that this generates exactly matches the supply of school seats. And it does this in kind of a monotone iterative fashion. You start off with very low cutoffs. Basically, any student can say, I want to go to any school. This is the proposal step, where students propose to their favorite schools. Now, some schools will be oversubscribed, so they have to reject some students at the bottom of the list. This means the cutoffs are going up until eventually they hit the market clearing levels. Okay, so this is deferred acceptance as it was introduced by Gale-Shapley. In order to use it in the school choice setting, we have to make some modifications. The first thing you might notice is that, well, in the school choice setting, schools don't have strict ordinal rankings. They have weak ordinal rankings, where we have these indifference classes. So how do we run deferred acceptance when we don't have the strict rankings? Well, what's typically used is something called deferred acceptance with single tie breaking. The idea is that we break ties within the priority groups at each school using randomization. We give each student a single lottery number and then use that single lottery to break ties at all schools. Okay? So for example, let's say I have two students, Alice and Bob. I want to figure out at school one who's higher on the list, Alice or Bob. We look at their priority. Okay, they have the same priority. So now we look at who has the higher random lottery number.
Wouldn't it be fair to reassign lottery numbers for each school?
Yeah, so the papers that I cited before were looking at precisely this question. What's the trade-off between single tie-breaking and what you're suggesting, which is called multiple tie-breaking, where we're using a new independent lottery at each of the schools.
Right.
And what they find there is that if the measure of efficiency that you're interested in is the percentage of students getting their top school, one of their top two schools, essentially top K for small k, then you should use single tie-breaking. Yes.
But I mean, none of this is as efficient if you have some cardinal.
Yeah, so I'm doing everything in an ordinal setting, but I agree that sort of.
Are there ways to extend what you're doing to cardinal?
So one thing you can do is that there's an LP formulation for basically the stable matching polytope, right? It doesn't quite work in our setting because it doesn't work once you have indifferences. But if you have this LP formulation, now you can start putting in different objectives that are cardinal in nature and solve for those over the set of stable matchings. But really, once you impose, yeah.
Is there something like that's sort of consistent with the like input nature? You know, the actual
Right. So you're talking about expression of cardinal preferences. That I think is a broader question than the school choice one specifically. But in the school choice setting, typically what you find is once you restrict to stability, if that's really the solution, the concept that you're going for, then generically there's only one outcome. Yeah, with the indifferences, yeah, now we have a class of outcomes. And yeah. Yeah. Yeah.
I'm asking is, could you, for example, add a kata-like feature
Uh-huh.
to your signal a single school at which you want priority in tiebreaking? Because we know that gets a constant factor approximation to the cardinal.
Yeah. That's a great question. Yeah.
Simple format to
Right. I'd have to think more specifically about how we would use the cardinal information, given the way that we've set it up. But I think we can. Yeah, I think there are ways to do that. We could talk about it offline. Yeah. Yeah. So everything I'm doing here is just in the ordinal setting. So I introduced to you deferred acceptance with single tiebreaking, and I want to mention that this deferred acceptance with single tiebreaking is what's currently used in practice, in part because there was this discussion about single tiebreaking versus multiple tiebreaking, and they decided they wanted to have more students getting to their top choice schools. So they chose single tiebreaking in New York City as well as in Boston and several other places. Currently, in the second round, they're using, again, this waitlist system to assign the vacated seats. And so at a very high level, our proposal, which is the Permuted Lottery Deferred Acceptance, is to just change up the lottery before sending out the waitlist. Okay? All right, so what they're currently doing is they're taking the tie-breaking lottery from the first round, using that as the school's strict preference ordering, and using that to build the waitlist for the second round. And so what we're proposing is, well, yes. So here I'm sort of conflating sort of everything that's maybe you can think of this as what's done in New York City kindergarten. This is what's done in New York City in the past. Yeah.
Well, my understanding is that the waitlist, they get rid of the waitlist, but then it's decentralized. You show up at the school, you still can get in. So that's kind of like a way of letting people kind of show their preference.
Yeah, so there are all sorts of ad hoc things that are currently done after March. What this means is that it is sort of a measure of how much do you want to go to the school. Are you willing to go through these loopholes where you submit an appeal or you go talk to the principal? Yeah, and so, yeah, so things like that which require some additional effort, maybe you would be able to signal which students really, really want to go to the school or have the time in order to be able to do such things. And so what we're proposing is, well, let's go back to the traditional school choice model of trying to maximize ordinal preferences. Yeah, and then what would we do systematically there? Okay, so this is our proposal. Another way to think about it is if I were to have all of this information about vacated seats right here, right after the first round of assignment, then what we're essentially proposing is collect all the updated preferences and now just run deferred acceptance again. Okay, but with two main modifications. The first is that we're letting students in the first round, we're giving them a guarantee in some sense. You're going to get a better school in the second round than your first round. You're guaranteed to stay in your first round assignment or be reassigned somewhere better. The second change we make is, as I already mentioned, instead of using the same lottery to break ties in the second round, we could use any new lottery in the second round. And so as I mentioned, currently they're doing something which we call the forward lottery. So when we do this single tiebreaking in the first round, we're again, the students who are lucky in the first round are again lucky in the second round. And so it's even more of this. You're lucky once, you're lucky forever. You could also imagine running a new independent lottery in the second round. There's no reason these two have to be correlated in any way. What we'll show is that the Permuted Lottery Deferred Acceptance mechanism based on reversing the lottery minimizes the number of reassigned students. That is, if we take now the students who were unlucky in the first round and make them lucky in the second round, this will actually help us also to relieve a lot of the congestion. Okay, and so let me flesh out what exactly we mean by this. Well, first I'll talk about why am I optimizing over the class of Permuted Lottery Deferred Acceptance mechanisms. Maybe I can do better outside of this space. And so we'll show that these mechanisms are in some sense the unique mechanisms that satisfy some desirable incentive and efficiency properties. On top of this, you might think, well, why is minimizing reassignment the right objective here? Maybe I'm interested in efficient assignment. Right? Maybe I want to maximize the number of students who are getting into better schools, and I can do that by just reassigning more students. And so what we'll show is that all of our proposed mechanisms actually give the same final assignment under natural conditions on aggregate demand. More precisely, for any individual student, they have some probabilistic distribution of possible assignments, which depends on the randomization in the first round. We'll show that for each individual student, this distribution is going to be the same no matter which mechanism we choose. And so that means if we were to use some notion of cardinal efficiency in the second round, if anything that's indistinguishable from the ordinal information that we've been given will be also equivalent, whichever mechanism we choose. And then if we were to use these other ordinal measures of efficiency, percentage of students getting their top, second, third choice, so on and so forth, those measures would also be equivalent. And so really, by minimizing reassignment, this is not affecting our efficiency. OK, so let me show you our model. We have n schools, S1 through Sn, an outside option Sn plus 1. Just think of Qi as the space or capacity that school Si has for students. We have student types, which encode both the student preferences and the school priorities. So that encodes their first round preferences, which is some ordinal ranking over schools. Their second round preferences, which is some possibly different ordinal ranking over schools. And then also this priority p theta, which you should think of as an integer valued vector. P theta 1, for example, could be 1. This tells me I'm in group 1 at school 1, where I live in the neighborhood and have a sibling. Or maybe P theta 1 is 2. I'm in group 2, where I only live in the neighborhood. Okay. So this is really encoding preferences on both sides of the market. You can think of this as sort of the input into the deferred acceptance. And so on top of that, we also want to keep track of this lottery number that we're giving students in the first round, because carefully relating this to the second round is what's getting us our results. Some assumptions. And so we do assume that we have consistent student preferences, in the sense that students' second round preferences are obtained from their first round preferences via truncation. Right? So the way to think about this is here, Alice prefers in the first round the blue school to the orange school to the yellow school. In the second round, she still prefers the schools in the same order.
So independence of irrelevant alternatives.
Yeah. So basically, you're thinking of
What?
The buses now.
Yeah.
choosing school buses, also an important question. Okay, so now we have the outside option, because Alice has found out which private school she can go to. She no longer wants to go to the yellow school. So you're thinking of just taking the outside option and moving it further up, or dropping some schools off the bottom of your list. On top of that, we also have a large market assumption. And so what we mean by this is we have a continuum model where we have a probability measure over these student types. And then we take the product measure with this random lottery that we're generating in the first round.
Could you, for cardinal efficiency, just like have a equilibrium rather than take just from the downwards to the left of the previous round?
That might be a kind of, it might disadvantage people who have sort of an unlucky lottery in the first round, because your endowment now has some value. It will.
Well, sure, that's true.
Yeah.
I agree. I mean, you could also redistribute that market.
Right. That's, yeah, an interesting thought. Why don't we take this offline? Yeah. Okay. The model timeline. Yes.
So is this, in what sense are the set of assumptions necessary? So for example, that allow second round preferences to be different, but only offer a guarantee with respect to them improving on their first round reports.
Yeah, so exactly. So really this consistent preference thing, we introduce it just to make the strategy proofness even have any meaning, right? Beyond that, all the results I'll show you about the sufficient condition, the equivalence. Yes, I think even the equivalence, we don't need to have this assumption. Yes.
Wouldn't it matter though if the reason, the source of the reassignment that you're trying to solve is like because people discovered new schools, or is it that the best school, the people that have that get in the best schools then have the best outside options? So that
Yeah.
They don't leave from.
So we provide a sufficient condition under which the equivalence is holding. The sufficient condition has the flavor of sort of aggregate consistency, right? So if something like what you mentioned happened, where all the students who left the system, where the students going to private school have just completely different preferences to the students who stay in the system, then these results might not hold. Yeah. I'll get to that more specifically in a few slides. Okay, going back to the timeline, we start out with the students' initial preferences and some priorities from the schools. We're assuming we're keeping the first round of assignment via deferred acceptance with single tiebreaking, after which point students find out about their outside options, and so this causes them to update their preferences by truncation. Now we take this updated preference information and we put it into a second round of deferred acceptance, where we're now proposing to change up the tiebreaking lottery before doing the single tiebreaking. And so now let me quickly answer the question of, well, why should I use this class of mechanisms? One answer is that they actually inherit the nice properties of the deferred acceptance mechanism. In particular, well, I already said that they respect guarantees. We're improving the assignment of students between the rounds. They also respect priorities. Again, this is fairly simple to see. Students with higher priority will be assigned over students with lower priority, because the second round is, again, deferred acceptance. On top of that, they're constrained Pareto efficient. Okay, so what is this constraint? Well, in general, you can think of respecting priorities as some sort of stability, and stability is in conflict with Pareto efficiency, right? And so this constraint is, if we need to respect priorities, how efficient can we get? More precisely, consider a cycle of students of the following sort. Every student in the cycle prefers the assignment of the next student. So student 1 prefers the assignment of student 2, and also has weekly higher priority at that school. So either that school is indifferent between the students or prefers student 1. If we had a cycle of such students, then we could just assign them all to the next school. And we could do that without violating priorities. So what we're saying is that when we run deferred acceptance with single tiebreaking in the first round, this is the notion of Pareto efficiency it satisfies. There's no cycles of this sort. Okay. And so we show that this is true for the first round of assignment, and in fact, then it's very simple to see as well that our Permuted Lottery Deferred Acceptance mechanisms also satisfy the same notion of efficiency, but now with respect to the modified priorities, where we've given students top priority at the school they were assigned to in the first round. These mechanisms are also two-round strategy proof in the large market model. Okay, what this means is that we know that deferred acceptance is strategy proof. It's a dominant strategy. It's in your best interest, no matter what anyone else does, to tell me your true preferences in the second round with respect to your second round assignment. On top of that, what we're showing here is that when you come in the first round, it's again a dominant strategy to report truthfully with respect to both your first round assignment and your second round assignment, as measured by your first round preferences and your second round preferences. Okay, we really need the large market here We have an example of where in a finite market this is no longer true, where you can misreport in the first round. This changes someone else's assignment in the first round. This changes the space of stable outcomes in the second round, and so then you're able to improve your assignment in the second round. Okay, so this is not true in a finite market, but what we show also is that the proportion of students who can successfully manipulate in such a way is vanishing in the size of the market. And in particular, because we have this randomization ex ante before you know your lottery number, the probability that you personally will be able to do that is also vanishing in the size of the market. On top of these mechanisms are in some sense also the only mechanisms that satisfy these properties. If we additionally impose, you should think of anonymity and averaging as some symmetry assumptions. And then we pin down the permuted lottery deferred acceptance mechanisms. Okay, so they have nice properties. They're the only mechanisms with these properties. And then from a practical perspective, these mechanisms are also simple to explain and implement to systems that are already using deferred acceptance. You can say, just run it again. You already have all the machinery set up from the first round. Okay, and so when I went and said this to Boston, they said, well, when would we run this centralized second round? After the start of the school year? And so, okay, that's a pretty reasonable question. Well, the great thing is, you could also implement a decentralized version of the permuted lotteries by using your waitlist systems. Right? Your first round will still be centralized, but now the second round of reassignment is decentralized via these waitlists. And by changing up the lottery before you send out the waitlist, you can reduce the amount of congestion in this decentralized round to a reasonable amount.
You just run, I mean, other places run it again, but they just not first day of school, but you do the application, you have matriculation, like you have to sign up.
Yeah, yeah.
And you can run it again then.
Yeah, yeah.
And then
so that's something else you could do.
Later. I mean, once you're always going to have people that just never showed up because they moved away or something.
Right, right. Yeah.
So Boston didn't like, what they didn't like about it? I don't know, they've been doing it for
so they already have several rounds. And so one question is also our model is sort of in this two-round setting, and so we had this proposal for changing up the lotteries between the first and second round, and the question was more, when would you change the lottery? Yeah, yeah. Yes?
Re-reporting, right? You need me to say my outside option materialize in a private school?
Yes, yes. Yeah, so via something like matriculating. Right?
Yes, that's what I was wondering, because it seems like there's no obvious sense. I mean, so there's some incentives I can improve, but if I'm already at my first choice school, I never report it.
Yeah, so one thing that they're doing in Boston in order to get this information earlier is they're calling the students this year. They're going to call up every student and ask, are you going to take your school? Or, you know, I'm not sure exactly what set of questions, but get some sort of signal.
The problem with that stuff is then the people that are the least, the poorest people, the hardest to help are the ones that their phone isn't working. And if they don't answer, then you kick them off the list.
No. So if they don't answer, you can't kick them off if they don't answer.
Tell you, actually, I'm going to go to another flight or I moved away.
Yeah. Yeah. So the hope is that the people who are likely to move away would have access to a phone, and you'll be getting a lot of the useful information early on.
Can I change anything here if I had a pretty good model, sort of like a standard ML model of predicting who's going to show up?
Yeah, I think that would. Yeah. This would also help with sort of the first round of yield prediction, those kinds of steps. And so then the actual reassignment stage would be a lot smaller. Right? Okay. So here are our results on optimizing over this class of mechanisms. Informally, we show that if a certain order condition holds, this is the kind of aggregate consistency condition, then all permuted lottery deferred acceptance mechanisms produce equivalent allocations. And now reversing the lottery will minimize the measure of reassigned students amongst equivalent allocations. The natural question is, what is this notion of equivalence? So we call it type equivalence, and we say two allocations are type equivalent if they provide each student with the same distribution for their final assignment. Okay, now because we're in a continuum model, we can actually think about it the following way. Here's a student type theta. So remember, this tells me both the students' first and second round preferences, as well as how much they're liked by every school. On top of that, I also have a given school, SI. And what I'm saying here is I'm comparing two reassignments, mu hat and mu hat prime. I'm asking, well, are they type equivalent? And this is equivalent to asking, for a type theta, are they assigning the same measure of that type to school I? Right? And so this is a statement about aggregate assignment of particular types. But because we have this randomization in the first round, this is also essentially giving me my probability if I'm type theta of being assigned to school I after some normalization. Okay. And so once we have this type equivalence, you'll notice it's a very strong notion of equivalence. Any measure of efficiency that you can obtain using just the ordinarily reported preferences, you can see that they're going to be equivalent once we have this type equivalence. The nice thing about this type equivalence is it also makes the minimization result fairly intuitive. The idea is that reversing the lottery shortcuts improvement chains. Okay, and so here was our example. This is a simple example where all the students have the same preferences. And also, let's just assume that all the schools are indifferent between the students. Okay, so we saw that when we used the forward lottery, well, you might not have noticed, but my wait lists were set up to use the same tiebreaking in the first round and the second round. Then what I was doing was I was going first to the student at school 3, asking if they want to move to school 2, and they move. And then asking the student at school 4 if they want to move to school 3. Okay, and this was occurring because the student at school 3 was in front of the student at school 4 in all of the wait lists. And this is because they were also luckier in the first round. They got to the more popular school. Let's imagine for a moment I reverse the wait lists before sending them out. Now when Alice goes off to private school, school 2 is going to first call the student 4, who's now at the top of their wait list. This is the unlucky student. In their first round, ask if she wants to move to school 2. She says yes, and now we'd move just one student 2 hops up her preference list, instead of 2 students 1 hop up their preference list. Okay, so what this type equivalence is telling us is that total number of hops is going to stay the same. But by shortcutting the improvement chains, we can minimize the number of students who are moving.
So I think when I learned addition in primary school, bunnies hopping, and I like the back row again. I don't really understand this.
Yeah, so once we have the type equivalence, we can do the same argument type by type. And it's really quite simple to see why this is minimizing the number of students that we're moving. And so the meat of the result is really, well, when do we expect this equivalence to hold? And so we provide a sufficient condition. We said that the order condition holds if, informally, schools have the same order of popularity in both rounds. What do I mean by this? There's some aggregate demand in the first round. This defines for me a most popular school, a second most popular school. I have possibly different aggregate demand in the second round. But what's important is that the school that was most popular in the first round is again most popular in the second round. The school that was second most popular in the first round is again second most popular in the second round. So notice it's just an ordinal condition. I'm not saying anything about how much more popular. Right? Just the order of popularity. And so before I present it formally, let me give you some examples of when we might expect this to hold. The running example I have is a common ranking. So obviously the order condition is going to hold here, right? Because school 1 is always more popular than 2, than 3, than 4. And so what we see is that, indeed, running the forward lottery, or reverse lottery, or any lottery in the second round gives us type equivalent assignments. That is, each of the 3 remaining students have exactly a 1/3 chance of being assigned to schools 1, 2, or 3. How they get there may differ depending on which of these lotteries we choose. But just from before the perspective of anything happening, it's a 1/3 chance of any school. Another example of when this condition might hold is when the departure is independent of anything else, of preferences, of assignment. And so if every student is independently with some fixed probability p leaving the system, then the second round demand is just some scaled down version of the first round demand. And so again, we expect the order condition to hold. Okay, but what precisely is this order condition? We define it in terms of the reverse lottery deferred acceptance mechanism. Okay, what we're saying is we run this mechanism. The outcome of deferred acceptance can be described in terms of cutoffs. Okay, and these cutoffs are going to give us our measure of popularity. More precisely, you can think of this C pi I as, given that I have priority type pi, this is how much all the schools like me, how lucky do I have to be to get into school I? Okay. Let's say in the first round I have to be luckier to get into I than j. What the order condition is saying is that under the second round, under the reverse lottery, I again have to be luckier to get into I than j. Yes?
Is there some version you can do that wouldn't just reverse, it can't be reverse the lottery? But would take whatever school, whoever ended up in the schools that were least popular, and just gave them top priority, and so forth downward. Like if you knew deterministically which schools were going to be most popular next, but they weren't the ones that were least popular in the first round.
So what we're requiring this condition for is to produce equivalent allocations, right? Saying that no matter how we use, whichever lottery we use, it's we're going to get the same sort of aggregate assignment in the second round, right? I think the intuition behind the reversing, if our only objective was to minimize the amount of change, I think reversing is doing essentially a similar thing to what you suggested, which is identifying students who would be able to do these big jumps, right? Yeah, so I think even if this condition were not to hold, you could still get some sort of weaker statement about minimization. Right? But this is really what we need to get the equivalence, exactly. Okay, and so again, what the order condition is saying is that the round 2 reverse lottery cutoffs are in the same order as the round 1 cutoffs. Okay, but again, also this is just some aggregate demand statement. Schools popular in the first round are popular in the second round. Okay. Let me quickly remark that when this condition doesn't hold, the mechanisms in general do not produce hyperequivalent allocations. This is probably not surprising. The counterexamples are not very big. You can easily construct them, but they're kind of hard to fit on a slide, so I'll spare you the details. What I do want to spend a moment talking about is why this condition is sufficient, how we can think about the problem. Okay. The main proof intuition is that instead of thinking about where students are assigned, we think instead of these virtual assortments. Again, this is the set of schools for which a student is above the admissions cutoff, or the set of schools that a student can choose to go to if they so wanted. So there are two nice things about the virtual assortment. The first is that it doesn't depend on my preferences, right? Once I have the virtual assortment, my preferences tell me where I get to go. Right? But it doesn't depend on the individual student's preferences. The second nice thing is that we've defined it here in terms of these cutoffs. And so now we don't have to think about individual student preferences. We just have to think about aggregate preferences and how they affect cutoffs. And we can do everything in the algebraic space of cutoffs. OK, and so what we'll show now is that all students actually have the same distribution of virtual assortments under all of these mechanisms. That will also mean that when we look at where they're finally assigned, because they have the same distribution over sets of schools they can choose from, they also have the same distribution over their final assignment. So in a setting where we just have one priority class, what this means is, well, in the first round, we have some possible set of schools you can choose from, all the schools except the first most popular, so on and so forth. What the order condition is buying for us is that in the second round under reverse lottery, we again have the same set of possible schools you can choose from. It's the same set of all schools, or the same set of all except the most popular, so on and so forth, because the order of popularity hasn't changed. Right? And so what this means, if I look at your overall virtual assortment, where you finally get assigned, which depends on both the first and second round, again, I get one of these n nice nested sets. Okay, and then the key intuition here is that on top of this, the reverse lottery cutoffs are in some sense maximally misaligned. Okay, I'm letting people do these big jumps, and so what this means is that if using the reverse lottery, I get the same order of popularity, then under any lottery, I get the same order of popularity. And so all this nice structure that we showed for the reverse holds for any mechanism.
So one question that comes up now, when in practice you don't actually do DA, you have like limited lists that you write down. So there's some strategy involved in what you write down on your list. So if you have a second round that gives you some benefit when you're unlucky. You didn't get into where you wanted to go. That could affect the strategy that people take when they write down their first subset.
Yeah.
I'm just wondering how. I mean, obviously, that's beyond what you're doing the first strategy. I'm just thinking in practice, that might actually be good because people just would write down their true, like their actual preference. They write down the things even though they might not get in, and they wouldn't put them down normally because they're strategizing. They could do it now, and then they have
another chance in the second round. This actually
would be like not so bad because even if they are super unlucky, then they would get bumped up.
That's a great thought. It actually relates to some work that I was doing with Brendan on sort of what if information acquisition is costly in these settings? People don't know exactly what their preferences are. And so maybe what we find is that something like a first round and then a second round can give you some information. Right? In the first round, you're finding out how likely you are to be able to get into all these schools, and then you can reduce some of the costly information acquisition, do better in the second round. And I think you're pointing out something similar. So that's a great thought. Thanks for pointing that out. Okay, and so we put all that together. We use all the cutoff things to guess cutoffs that match up all the virtual assortments. Because the reverse lottery cutoffs are maximally misaligned, we can use some sort of monotonicity arguments to show that actually our guesses are correct. Everything goes through, and every student is getting the same distribution of virtual assortments. Okay, and so this is for one priority class. And then we also have some additional techniques to reduce the general case to this particular case. Okay, let me not go into those. I wanted to spend just 2 minutes showing you the results of some simulations that we did on New York City high school data. And so what we have is we have preferences from the students in the main round of admissions from 2003 through 2011. What I'll show you today is just from 2004, 2005, and the following enrollment in the following academic year. Okay, what we do is we read off the students' first round preferences as well as the school priorities and capacities directly from the data. But we don't have centralized information about their second round preferences, and so we simulate these. We can use the enrollments. We see that some students don't enroll in any public school, so we assume that they leave. Or we see that some students do stay in the public school system, and so we assume that they retain the same preferences in the first round, in the sense that they're willing to be upgraded to any school that they preferred to their first round assignment according to their first round preferences.
People who leave, I guess they couldn't prefer some school.
Right. Yeah. So there are some assumptions that we're baking in here, but this is just to get a sense for how well does our theory translate to something where we're at least incorporating true priorities, right, and some true preferences. We still just assume that they keep the same preferences. Yeah. I don't have the numbers for how many students were like that, but there were definitely some students like that. Okay, so given this preference information, now we can simulate a family of permuted lottery deferred acceptance mechanisms. They're parameterized by this parameter alpha. For the purposes of the talk, you just need to know that when alpha is positive infinity, I get what's currently used the forward lottery, using the same lottery again. If alpha is negative infinity, I get the reverse lottery. And now I have also all these different values of alpha on the x-axis. On the y-axis, I'm showing you the number of reassigned students. Okay. So you can see that by moving from the forward to the reverse, I can more than halve the number of reassigned students from just over 7,000 to just over 3,000. Yes?
Can you plot the number of individual reassignments rather than reassigned students? I can imagine there are students who got reassigned again.
Great. Yeah, so what you're saying is there may be, okay, so we did all these simulations when we were thinking of just what's the change if we were to run 2 centralized rounds. What you're pointing to is if the second round is decentralized, what does that look like? And actually we had the same question, but we're still running those simulations. So I don't have those numbers for you yet. Yeah. On top of that, we also wanted to look at the efficiency of the different mechanisms. So our type equivalence is saying for every individual student they get the same distribution of assignments, but here that's a little hard to measure. And so I'm just showing you the percentage of students getting their top choice school, percentage of students getting one of their top 2, top 3, so on, for different values of alpha. Okay. You can see that 50% of students are getting their top choice, and amongst all these values, there's a difference of at most 1%, and that difference is actually decreasing as we go to higher k. Okay. On top of that, I also want to make the same remark that this is just looking at the allocative efficiency of the final assignment, but what we're really interested in is how well does this decentralized version do? How many, maybe, so what we're showing is something that may not ever be reached, right? Because we cut off the second round after 2 months in, and so you should think of the numbers at the top as being a little more optimistic than the numbers at the bottom, because there's more reassignment at the top than at the bottom. Right? It might take longer at the top to reach this final number. And so we're running some simulations to see, to quantify that a bit more. How many essentially phone calls, how many times do you have to go down the list, how many times do individual students have to move under all of these different values of alpha. Okay, so in sum, our simulations match our theory. These mechanisms give similar allocative welfare, but reversing measurably minimizes reassignment. And this occurs even though the order condition, which is a very technical and somewhat brittle condition, doesn't hold exactly on the data. Okay, so in sum, what have I said today? Well, if we want to design a reassignment mechanism in school choice, what I've said is essentially reverse the lottery. Just do what's currently done, but before sending out the wait list in the second round or whatever in the second round, reverse the lottery you used to do the tiebreaking. More specifically, we have a characterization theorem that shows if you want desirable incentive properties as well as some other properties that the first round of assignment has, then you need to use a Permuted Lottery Deferred Acceptance mechanism. The key idea is that within this class, we can correlate the lotteries between the 2 rounds to let us control the amount of reallocation. On top of that, we also have a type equivalence result that shows that all of these mechanisms give equivalent allocations in the second round. And so then the only question is how much does the first round differ from the second round, and reversing the lottery will minimize the amount of change. We also have some simulations that show that even though this was all done in a theory land, this may have some implications for practice. And so I know I'm going over time, so I just want to tell you very briefly that we did talk to New York City and Boston public schools. Here's one of the slides I used in our little pitch. The result of that is that both systems are actually very excited about this idea because it's a small change but can have large impact. And so with New York City, they didn't want us to do it on all, well, first they didn't want to reintroduce waitlists and then make all these changes to all 80,000 high school students. So they said, look at the kindergarten, where we're already using waitlists. Let's look specifically at kindergarten gifted and talented, where, okay, just take a moment for that to sink in. But so the top 1% of kindergartners, there's currently a lot of this congestion going on where there's not enough space for all of them to go in these programs, and the lucky ones are getting shuffled amongst the programs whilst the unlucky ones wait. Okay, and so they said, we'll give you the data for this. Run your experiments again. If they look similar, we believe they will. We'll run our simulations. If the simulations look the same, then they'll let us do a field experiment. Yeah. And then moving forward, we also have some theoretical extensions looking precisely at issues of, well, what if there are students coming into the system? What if my preferences aren't exactly consistent? Yeah. I also have some thoughts on my future research agenda, but since I'm running low on time, let me just say that overall, my goal is to design smoothly operating marketplaces using techniques from economics and game theory, computer science, and operations. I think there's a lot of opportunity to work on all of these with people here. Thank you.